Anyway, let's start. And today we're glad to have Zihong Chen, same as Peter Chen, from MIT, and he will speak about exponential type conjecture for quantum connections. So please.
Yeah, thanks for the invitation and introduction. So I will talk about the exponential type conjecture for quantum connection. So feel free to ask questions if you are confused about anything. Most of the talk, hopefully, it will be about elementary algebra and ordinary differential equations. So here's a rough outline of the talk. I'll start by introducing some concepts in differential equations in characteristic P. So most notably, this Katz's local monodromy theorem. And then I'll talk about the definition of the quantum connection and what this conjecture is about. So one of the central idea of proving this conjecture is to use certain equivariant operations. And I'll demonstrate how this works on the mirror B side, where the structure is particularly simple. And finally, I'll introduce what's called the quantum Stinger operations and how this relates to the proof of the conjecture. Okay, so let's start with some basic ODEs. So I'll consider a base coefficient ring R to be an integral domain. And in this talk, I'll consider formal connections on this formal affine line R join a formal variable T. So explicitly, we have a connection just on the free vector bundle on our direct T of rank n. Okay, so this nabla d over dt is equal to d over dt plus some connection matrix A. So we can write it out. D over dt plus, it can have some singularity, say of order small n. And in general, it will look like this. Okay. So we can have an element of GLN of our double bracket T where we allow, sort of inverse powers in T to act as gauge transformations of these set connections. And the action is given on the following. So given such a phi, I can pull back the connection. And the connection is given by the following formula. D over T plus a new connection matrix. Which is phi inverse A phi plus phi inverse, d phi over dt. And now let me introduce a definition. So for any such kind of connection, the best possible scenario is when the matrix A has no inverse powers T, or in other words, it's a regular connection. But usually that's not what happens in nature. Most examples that arise from geometry will have some singularity. And somehow the best possible singularity is the so-called regular singularity. So the definition is the following. So nabla d over dt has regular singularity if there exists a gauge transformation P as above with potential poles such that, move this part down a bit. So there exists a gauge transformation such that the pullback connection has connection matrix with a simple pole. Okay, so you might start with a connection which has bad poles, but as long as you can find a gauge transformation which puts into this form, which is a simple pole, it's called regular singular. So now it comes with a question, which is, how do we ever check if a connection has regular singularity? Because just from a definition, we have to really find this gauge transformation that puts it into the correct form. But there's a very nice answer to this question due to Katz. So the answer is we can give a criterion of regular singularity by reducing the connection mod p. So now,
if you can do that.
If you can do this, yes. If your coefficients allow you to reduce mod p. Yeah, that's a great point. So let's reduce mod p if the coefficients allow. So well, let me go in more detail what this means. Okay, so for this, let me first introduce a notion of called p curvature, which is an invariant of a differential equation in characteristic p. So what is the general setup? Let's fix a field K of characteristic P and let X be a variety over K. Let's further fix nabla E, a vector bundle with connection on X. Together with D, which is a vector field, or a derivation of OX, which is K linear. So the P curvature of nabla along D is the following endomorphism. So I'll denote P curvature by F nabla along this vector field D is defined to be the pth iteration of the covariant derivative along D minus the covariant derivative along the pth iteration of this vector field D. So we can check that this is actually an OX linear endomorphism of E, just like in the case of usual connection. So intuitively, what this is measuring is this P curvature is measuring how the covariant derivative nabla is not compatible with taking P's power. And it is a unique phenomenon in characteristic P. So now, what is the statement of the local monodromy theorem? So here's a setup. Let's fix the space coefficient ring R to be a so-called global affine variety. So namely, it is a subring of the complex numbers, which is finally generated as an algebra over the integers. Okay, so in particular, it is a characteristic zero ring. So for instance, what are the consequences of this? So this implies, for instance, that R has infinitely many maximum ideals, and that modulo each maximum ideal, it is a finite field because of this finite generated over Z. So this is how we can talk about reduction mod prime P. So what is Katz's theorem? The theorem says that if you have a connection over the formal alpha line where R is a global affine variety, then we can base change this thing to the fraction field of R and do a T completion. So to check that this connection is regular singular, it suffices to check that if I reduce this connection, mod P, meaning tensoring over this residue field, it has nilpotent P curvature. For all maximum ideals.
Sorry, okay, to understand, you say that you want to check that something is regular, yeah, but first you have to define it, because your definition with gauge transformation, I'm not sure that it's kind of correct definition if you work over an arbitrary field of finite over an arbitrary field of.
So R is a ring of characteristic zero. In particular, fract of R is a field of characteristic zero.
Yeah, but let's see. Yeah, so then is it equivalent to the existence, let's see, is it equivalent to the existence of the gauge transformation which make the pole of order 1 over an arbitrary field of characteristic 0?
Yes, I think I'll just take that to be the definition of what it means to be regular singular. So
let's see.
Can I understand?
Yeah,
this?
maybe you're right.
So if
yeah.
you replace the fraction of R by C, simply by C, so go back to a complex case, so the regular singularity will be clear.
Right, so you can do this, but I think this result hold just over frac R. So in particular, you can find a gauge transformation phi with coefficient just in the fraction field of R.
Yes,
that,
I understand.
Yes, that makes it regular singular. Yeah. Thanks.
Yeah, okay, yeah, it will work. Yeah, okay.
Okay. Right. Are there any other questions so far? Okay, great. So this gives the criterion. So to check regular singularity, let's reduce this connection mod P and check if it has nilpotent P curvature. Okay, so let's now move on to the main topic, this talk, which is quantum connection and exponential type conjecture.
Yeah, and maybe to go back for a second, I mean, an alternative way to think about a regular singular connection is to look for the stable lattice. Is it, I know this of the field of characteristic 0, is it the same over finite field that there is an nabla invariant lattice in the E with a scalar change to the fraction field?
That's a great question. So
it seems to, it looks like it should be, but I'm not.
Yeah, I'm not sure. So
sure,
I think
because it's another way to check that something is regular singular is just to find this invariant lattice.
right, but I'm not sure if people really. I'm not sure like if regular singularity is a good notion in positive characteristic. Maybe.
Yeah. Okay. Anyway, it's kind of it's a side question. So okay, go ahead.
Okay. Okay, so let's move on. Okay, so let me talk about the quantum connection. So the geometric setup is I always fix a 2n dimensional symplectic manifold, which is closed monotone. So let's recall, so monotone for me just means that the class of the symplectic form is equal to the first string class inside dropper 2. Okay, so this is a scenario where all the technicalities of Floer theory and Gromov-Witten theory are the simplest. So under this setup, let QH of X in R be the quantum.
Since you kind of first Chern class of what?
Sorry, of the tangent bundle.
Yeah. Okay.
So let's define the quantum cohomology of X with coefficient in R to be just, well, as a R module, it's just the singular cohomology of X in R, but it's equipped with the quantum product. So this, I won't recall the definition, but I'll just say it's defined using three-pointed genus 0 Gromov-Witten invariance. And this gives a multiplicative structure, which is called the quantum cohomology overall. So there's a connection on the equivariant singular cohomology of X called the small quantum T connection. So this is a connection on, so it's a connection on H upper star X with coefficients in R adjoins formal variable T. And it's defined by the following formula. So nabla QH I'll just consider the differentiation in the direction t. So it's called the quantum t connection. It's equal to d over dt plus, so there's a quadratic pole, which coefficient is given by quantum multiplication by the first term class of the tangent bundle, plus a simple pole, which is this mu, and this mu is some kind of grading operator. And its definition is combined following. So mu restricted to, say, degree q singular cohomology is defined to be q minus the complex dimension of x mod 2, divided by 2. Okay, so that's the definition of the small quantum T connection. Essentially, it packages information about, three-pointed Gromov-Witten invariance of the, symplectic form omega, or equivalent in this case, the first term class. So we can take a spectral decomposition. Okay, so over a suitable finally generated extension of Z.
And the dimension n here is just the real dimension, right?
Sorry, so yep, so this
Dimension.
n, this small n is the complex dimension
A complex dimension.
of
Okay.
X.
It's not necessarily even. Okay.
Right.
Thank you.
So over a suitable, finally generated extension of Z, we can have a generalized eigenspace decomposition of this multiplication by the first term class, which I'll denote the lambda eigenspace by H star XR sub lambda. So here's an sort of elementary lemma called elementary splitting. Okay, so what is the statement? So over such an R where an eigenspace decomposition exists, if we further assume that the difference of two distinct eigenvalues is invertible in R, then there exists a unique decomposition of this H upper star XR adjoint T, also with summons labeled by the eigenvalues first term class, with the following property. So first, when you restrict each lambda summon to t equals 0, you get back the lambda eigenspace of C1 star. And the second property is that this decomposition is respected by the connection. And these two properties uniquely characterize this decomposition. So I won't give the proof here, but the proof, sort of by induction. So we construct a step-by-step gauge transformation that puts your connection matrix into this block diagonal form. So
By induction on what, on the cohomological degree or?
sorry. No, it's not induction by on cohomological degree. It's induction. You can think of this as induction on powers of T.
Okay.
So right, because the gauge transformation is like a power series or Laurent series in T, and you induct on its powers.
Mm-hmm. So that means you could just do an infinitesimal equation
Yes.
of high
So
powers T, right?
yeah, so everything, like all the gauge transformations, the connection is considered as like a formal gauge transformation, and this decomposition is like also formal. Okay. So what this decomposition brings you is that because of this property 1, that t equals 0 part of this decomposition is just the eigen decomposition. If you restrict your connection to this lambda summand, then it is gauge equivalent to the following form. So you have d over dt plus some term which has a quadratic singularity, but this quadratic singularity, it has this form which is equal to lambda times the identity plus this m lambda, which is a nilpotent Jordan block. So this is just the lambda component of the Jordan decomposition. Nilpotent Jordan block plus some extra terms which has at most a simple pole. So let me just write this gauge transformer connection into the following form. It's equal to this part, I'll call it the principal part, tensor with this, which I'll call the residual connection, associated to lambda. Okay. Let's denote this by nabla QH lambda with a twiddle, okay, d over dt. So again, this is a connection. This residual connection is, a connection with a potential quadratic singularity. But people expect that this connection should really have regular singularity. And that is a statement of the exponential type conjecture. Okay, so over the complex numbers, the conjecture says that for each eigenvalue of C1, the residual connection, tilde nabla, should have regular singularity at t equals 0. So somehow from the explicit form this connection takes, we see that the quadratic pole term is a nilpotent matrix. So perhaps this gives us hope that something like this conjecture should hold. But let me just give one example why this conjecture is not trivial. Example. Okay, so this is from Kontsevich-Katzarkov-Pantev. Okay, so consider the matrix, consider the connection d over dt plus 0, minus 1, 0, 0 for t squared plus 0, 0, minus 1, minus a half over t. Okay. So this is a connection with a quadratic singularity with a nilpotent quadratic pole. But this connection has irregular singularity. At t equals 0. So which means that really this property that the residual connection of the quantum connection has regular singularity should come from the geometry of Gromov-Witten invariants, not just from some elementary algebra.
Yeah, but at least it's a necessary condition for the coefficient matrix to be nilpotent. Because if it's semi-simple, then there is no way.
That's correct.
Yeah.
So the exponential type conjecture is, for example, trivial if you know that C1 star can be diagonalized or is semi-simple. So it's only interesting when the C1 star has some non-trivial.
By the way, this quantum product, but C1, it's, what is it? It's semi-simple in quantum case, or?
So we know that the quantum cohomology ring itself is generically semi-simple. In particular, that implies C1 star is like generically semi-simple, but there are specific examples that arises where this thing is not semi-simple, and that is the case where we'll be interested in.
Yeah.
Even though the cohomology ring is semi-simple, doesn't mean that the elements are semi-simple acting on it.
So the quantum cohomology being semi-simple certainly implies C1 star is semi-simple, but the converse is not true. Yeah, if C1 star is semi-simple, it's certainly far weaker than saying that the quantum cohomology ring is semi-simple.
And because the quantum cohomology ring is semi-simple or not, but the elements multiplying, that can be matrix algebra. You can have lots of not semi-simple matrices by left multiplication.
No, yeah.
Okay, well, yeah, I'm sure that's the geometric part.
Okay. So let me just make a few remarks about, the history of this conjecture. So this conjecture first appeared in this Hodge theoretic aspects to mirror symmetry of Kontsevich-Katzarkov-Pantev, and later in this paper on gamma conjecture, Galkin, Iritani. So the first, major progress to its conjecture is made quite recently by the work of Kontsevich-Katzarkov-Pantev in the series 2 papers. So they proved the conjecture for all closed monotone X, which emits a smooth symplectic divisor Y, which represents the Poincare dual of the first string class, and such that the complement of this divisor is Weinstein. Okay, and their paper is kind of invoked. So is the main tool in their paper. There are a lot of significant ideas in their paper. So there's categorical Fourier Laplace transform. There's this kind of Foreman-Sheridan definition of symplectic homology. So there's various ideas in their paper, and they prove somehow they definitely prove much more than the conjecture, but their proof requires this assumption. And I guess the goal of my talk is to give somehow a simple proof of this conjecture for all closed monotone X using this kind of reduction mod P idea that does not require an extra assumption. Okay, so this is the main result, my paper. So the basic strategy is to reduce mod P. And to say more detail, by Katz's theorem, to prove that each residual connection, this tilde nabla QH of lambda has regular singularity, we just need to show that it has nilpotent P curvature when reduced mod almost all prime P.
By the way, before you going into geometry, do I remember correctly that if it has nilpotent P curvature, then somehow solutions are algebraic functions?
That's not quite correct. So if you know that it has zero P curvature, then the formal solutions are
it has to be zero. Okay.
Yes, but that's just a local statement. The global statement is like the Gromov-Witten conjecture, which is still widely open. And I'll also mention the case where you actually have zero P curvature at the end of the talk, if there's time. So, okay, so now our goal is to prove that this residual connection has nilpotent P curvature. But recall that this residual connection is given by the usual connection restricted to the lambda component minus lambda. In particular, its P curvature is just the P curvature of the usual quantum connection, subtracting the P's power of lambda. And equivalently, this is the statement that we want. Okay, so we want to prove that this expression is nilpotent for almost all prime and for all lambda. Okay, so as I said at the beginning, the key idea to proving this is to relate P curvature to certain equivariant operations on this equivariant quantum cohomology. To demonstrate this idea, let me just pass to a mirror situation where these kind of operations are particularly easy to define. So what is a mirror situation? So we know from, I guess, mirror symmetry that the mirror to a closed monotone simply manifold are often Lindau-Ginsburg models, meaning it's a algebraic variety Y equipped with a superpotential or some kind of function to the affine line. So let me consider a very simplified setup. So take Y to just be, I want Y to be the affine n space over Q bar. And let me take the superpotential and let me constrain the property that the superpotential has a unique critical value, which is 0. So in particular, the matrix factorization, well, it usually decomposes into several pieces, corresponds to the critical values of W, but now it's just one piece. And there's an associated cohomology called the twisted theorem cohomology, which is defined by the following. You consider differential forms on Y, adjoining again is formal variable T of degree 2, but with a differential given by minus T times the theorem differential plus wedging by D of W. So on this, on the cohomology of this chain complex, there lives a connection, which is analogous to the connection, the quantum T connection we considered and it's given by the following. So the connection is d over dt plus w over t squared plus this gamma over t. Plus gamma is again an analogy of a grading operator. In particular, gamma restricted to degree q differential form is defined to be just multiplication by q over 2. And why do we consider this connection? So there's a result of Shlerov that says the twisted theorem cohomology equipped this connection is isomorphic to the periodic sigma-homology of the category of matrix factorizations equipped with the Katzarkov-Pantev connection in the t direction. And the latter gadget is sort of what allows one to relate this B-side connection with the A-side connection via homological barrier symmetry. Okay, so what is the B-side statement here? So the B-side statement is that
it's a good question. The Shklerov is who's the Shklerov? Is the Dimash Shklerov?
Yes, it's Dimash Shklerov. It's my graduate student, and he left mathematics.
Great. Okay. So so the theorem of Sabah and Saito says that this connection associated to the function w has regular singularity at t equals 0. So there are general proof uses also for Laplace transform and their D modules, but let me try to give a simple proof that uses the kind of reduction mod p method. Okay. So how does the proof go? So again, we use Katz's theorem to reduce this regular singularity to checking the opotence of p curvature for almost all p. Now, there's one thing which is really nice about this B-side situation, which is we can actually compute p curvature very easily. So let's do the computation. So the p curvature, okay, so for simplicity, let me consider the p curvature along the direction t squared d over dt. By definition, this is just, well, nabla d squared d over dt to the pth power. Okay, so here I use the fact that the pth iteration of this vector field t squared d over dt is actually 0. Now, by definition, this is t squared d over dt plus w plus t times gamma to the pth power. Now, obviously, this w, well, it's just multiplication by the function, so we can pull it out because it commutes with the other parts of this expression. And the observation now is that this extra term is actually 0.
I thought the curvature was the difference.
Yes, that's what I mentioned before. So the p curvature is difference of this with this thing, right? But if you compute that what is the pth iteration of this vector field, you can see that this actually is 0. So that's something you can check. So in fact, this p curvature actually only have one term. Okay, so why is this latter part of the p curvature 0? So this comes from the following elementary observation. So gamma, of course, is just a grading operator. It takes value in half integers. So let me assume my prime number is bigger than 2. Okay. So in particular, if you have, so that implies that if you just have any number, which is half integer, then x to the pth power minus x is 0 when reduced mod p. And if you expand out the second term, you'll see that it has to be 0 for the reason I just mentioned. Okay, so particularly we computed the p curvature to just multiplication by the pth power of this function w. And now we would like to show that this operation is nilpotent. And the key idea is to interpret this kind of multiplication by w to the p as a kind of equivariant operation.
Sorry to interrupt you. So for the sum of this t squared dt and the operator and also the t gamma, are they commuting?
They don't compute, but you can sort of.
Do they commute?
They don't commute. They don't commute.
Okay.
But what we can do is that you know that p curvature is a linear operation. So in particular, if you can pull this factor of t out, okay, that will result in a multiple of t to the p in your p curvature. But then the expression t dt, t d over dt plus gamma, these two expressions really commute. So you can compute the p curvature in that way.
Thank you.
Okay. Okay, so now let's consider an action of functions on y on this theorem cohomology, the twisted theorem cohomology. So where a function f acts by just multiplying a twisted theorem differential form by the pth power of the function. Okay, so it's well defined because the theorem differential of the pth power function is p times f to the p minus 1 of df, which is 0 in characteristic p. So, okay, so this is something which is like the key computation, but it's somehow a tedious but straightforward computation, which I won't do during my talk, is that you can check that this action, act P, descends to an action of the Jacobian ring. So if you quotient your function field by the ring of partial derivatives of W, then this act P actually factors through this ring. And once you have this, somehow the statement is very easy. Why? Because you observe that this P curvature is, which we computed to just be multiplication by W to the P, is just action of this element W viewed as an element of the Jacobian ring of W. Okay, but of course, act P of W or act P of this is multiplicative in this entry. So in particular, to check that this act P of W is nilpotent, it suffices to check that W is a nilpotent element of this Jacobian ring. Okay, but this follows from Nelson-Lansens. Because assume that W has a unique critical value 0. So so in particular that implies that it has to be some power of it has to lie in the ideal generated by its partial derivatives. Okay, so that's the proof. So to summarize, I first computed the P curvature of this connection, and then I related this P curvature to some kind of equivariant operation, this act P. And then I reduced this statement about nilpotence of P curvature to nilpotence of a certain element in the Jacobian ring. And this is the idea I want to carry over to the case of quantum connection. So somehow the key extra input we need is to, what is the analog of this act P or this equivariant operation on the A side? And it turns out that these are so-called quantum string operations, which I'll introduce next. But are there any questions before I can move on? Okay, great.
Can the gradient operator be divisions by anything other than z over 2? Can it be z over 3, for example?
So the question is, so the definition of the gradient operator is just multiplication by the degree over 2. somehow this vector of 2 is somehow it's just there.
I mean, can that be generalized, or what's the
Okay, so
significance?
So what's the significance? So I think the reason why you have this over 2 here is because this variable t has degree 2. So in particular, if you want to consider like total grading on the equivariant, say, quantum connection, so what would you do? So you would first say, I have the grading in singular cohomology. And I also have the grading coming from this t variable. But each t variable give you degree 2. So somehow you normalize, and this tells you that you should sort of weight the grading in singular cohomology by a half. Does it answer your question?
Yes, thank you.
Okay, thanks. Great. Okay. All right, so let's talk about quantum string operations. So these are special kinds of operations on equivariant quantum cohomology when your coefficient field is a field of characteristic P. Okay, so in particular, the definition of quantum string operation, it is a map denoted by Q capital sigma. So it's an action of quantum cohomology of X with coefficient in K on this kind of equivariant singular cohomology. So how is it defined? So let me first draw a picture. Okay, so this is the picture. I consider my domain to be this genus 0 or just a CP1, but I have some incidence conditions. So first I fix this one input at 0. So this is incident to the equivariant singular cohomology alpha. And then on the equator, I fix this piece roots of unities, and each of them is incident simultaneously to this class B, which I X by. And then I consider an output, which is at infinity. So I consider all J-homomorphic maps from this domain to my targets in manifold X. But somehow I want to count this kind of moduli space in a way that's Z mod P equivariant. Okay. So I want to count these things Z mod P equivariantly, where the Z mod P acts on the domain by just rotating the CP1 along the equator. So to be more precise, I want to fix perturbation data, which are domain dependent. But they also, okay, so the perturbation data is just some map from the tangent space of C to the tangent, or the tangent bond of C to the tangent bond of the target manifold. But they would be dependent on an extra parameter W lying on S infinity, or viewed as the universal bundle of B Z mod P. So after fixing, so what is the requirement for this kind of perturbation datum? I want the perturbation datum to be also Z mod P equivariant with respect to the Z mod P action on my domain CP1 and with respect to the Z mod P action on S infinity. So after fixing this kind of equivariant Floer data, I can count solutions to the Floer equation where this extra variable, this equivariant variable W, is constrained on some kind of distinguished cells in EZ mod P. So these cells, you should think of them as those cells which, when you further descend to the quotient by S1, they should form like the canonical, the standard cells of CP infinity. Okay, and those operations give me what I call Q sigma of I. And finally, I will define Q sigma to be this kind of power series.
Is it obvious that for constant maps you get this standard Steenrod operations?
Yes. So if I consider, yes, exactly. So in particular, if Q equals 0, meaning if I only take like constant holomorphic curves, I should get just classical Steenrod. So that would be exactly like this kind of definition of the classical Steenrod operation. Okay, so what are some properties of this quantum singular operation? So first one is called quantum Katz relation, as it generalizes the classical Katz relation for singular operations. So it's that Q sigma of A quantum couplet B is equal to the composition of Q sigma A and Q sigma B. In other words, Q sigma is an algebra action of the algebra of quantum cohomology on this equivariant singular cohomology. The second property, which is very important to us, is so-called covariant constancy. Okay, so what does this say? It says that Q sigma A for any A commutes with the quantum connection. And this is a result due to Seidel workings. Okay, so the two key results that allows us to prove this kind of regular singularity of this residual quantum connection are the following. So the first result is, a result that relates quantum singular operations to p curvature of the quantum connection, and the results due to Paul Seidel, and is inspired by the work of J. He Lee, who considered this kind of p curvature of quantum connection and quantum singular operation arising in a situation that has interest in representation theory. So the so-called symplectic resolutions. So that's where this kind of p curvature quantum singular business first arises. But the statement is the following: is that the p curvature of the quantum connection, subtracting Q sigma of the first string class, is nilpotent operation. And here's the idea of proof. So first of all, you first restrict the classical part, Q equals 0, of the p curvature and the quantum singular operation. And you can check that both cases is equal to the classical singular operation of the first string class, which is this explicit kind of Artin-Schreier expression. And secondly, you check that when you restrict to t equals 0, so where t is this equivariant variable, then both the p curvature and the quantum singular operation is just the p-fold quantum multiplication by the first string class. Now, so you check that the base cases of these two operations agree, but then by covariant constancy, you can show that the difference has to, vanish in. Okay, so the difference has to contain only terms where the power of t and q is larger or equal to t times q to the pth power. Okay, but then you observe, just look at degrees. So both operations have degree 2 times p. But you see that this term, so the raised degree, like 2p plus 2, because t and q both have degree 2. So in particular, in this expression for their difference, the degree that is contributed from the degree of singular cohomology has to be decrease by at least 2. But of course, singular cohomology is concentrated in abundant range, so that proves the difference is nilpotent. Okay. So I want to mention there's a very recent enhancement. Okay, also due to Paul. In fact, this p curvature is not just nilpotent, or the p curvature minus the q sigma c1 is not just nilpotent, but they're actually equal. Okay, so that's a very recent development of this result. Okay, so that's the first part of the argument. The second part is that this q sigma, this quantum singular operations, is compatible with the special splitting of the quantum connection. Okay, so what do I mean? So recall that previously we had this decomposition of the equivariant singular cohomology into components labeled by the eigenvalues of the first string class such that this decomposition is respected by the connection. Okay, so now you take a element B inside the lambda eigenspace of C1 star. You take an alpha, which lies in this lambda prime decomposition component of the decomposition of the connection, such that lambda is not equal to lambda prime. Then the action Q sigma of B on alpha has to be 0. Okay, so somehow the action is orthogonal with respect to this spectral splitting. So how do we prove this? So the idea is, again, kind of simple. So you look at the collection of quantum field operations. So where this E lambda is just a projection of the unit onto lambda eigenspace. So just the lambda idempotent. And you consider Q sigma of these E lambdas as a collection. Now these collections satisfy the following four properties. First of all, they split the identity on the endomorphism. Secondly, if you can consider like composition of two of them, it's equal to 0 if lambda is not equal to lambda prime, and it's equal to just one of them, Q sigma E lambda, if lambda is equal to lambda prime. So in particular, the first two properties says that all these operations, so these two properties imply that these things are just projection operators. But there are very special kind of projection operators because so property 3. So when you restrict to the t equals 0 part, the Q sigma is just quantum multiplication by the p-fold quantum product of E lambda, which is the same as projecting onto the lambda eigenspace of C1. And the fourth property is that each Q sigma commutes with the quantum connection. So these two properties, together with the first two, implies that, in fact, Q sigma is actually projection onto this lambda component of the splitting of the connection. Okay. But now you take an arbitrary cohomology class inside the lambda prime component of the eigen decomposition. So by quantum Katz relation, you see that if you take the composition of Q sigma B with Q sigma E lambda, where lambda is not equal to lambda prime, then they compose to 0. But because this is projection onto, but this term is just projection onto the lambda component, this statement is just an immediate consequence. Okay, are there any questions so far? Okay, great. So now we can conclude the proof. So recall that we need to show that this difference between the lambda component of the p curvature of the quantum connection minus lambda of the p is nilpotent. And by 1, it suffices to show that the difference between this quantum string operation of C1 with lambda of the p restricted to the lambda component of the connection is nilpotent. Okay, but now let's just see how it works out. So this minus lambda of the p restricted to this lambda component is equal to, so now I use property 2, which says that the Q sigma is compatible with spectral splitting. It's equal to Q sigma of C1 lambda minus lambda of the p restricted to this lambda component, where C1 lambda is equal to the projection C1 onto this eigenspace. Okay, so I'll need some extra space. Oh, sorry. Sorry, what difficulty? Okay, so let's continue the argument. So this term is further equal to cube sigma C1 lambda minus cube sigma of lambda times the lambda idempotent restricted to this component. Okay, so this is because, okay, just like Cauchy operations, the quantity operation is so-called Frobenius linear. So when you multiply this part by constant lambda and you pull it out, it gets multiplied by the p's power of the constant. But now let's combine these two terms. Okay, so now we observe that we are exactly in a situation that's similar to this B-side situation. I've sort of transformed this kind of P curvature into expression relating concerning the quantity operation of a special class, which is here. But this class is nilpotent. As a class in the Kontsevich-Katzarkov-Pantev. And that's just by definition of the lambda generalized eigenspace of C1. But then we're done. Because Q sigma is a multiplicative action. So if the element you're acting by is nilpotent, this action is nilpotent. Okay, so somehow that finishes the proof of this conjecture. So maybe in the remaining 2 minutes, I want to just mention one slight enhancement of this exponential type result, which is the following. So recall that I mentioned that Paul recently obtained a proof that yes, Paul proved that, in fact, the P curvature of the quantum connection is actually on the nodes equal to Q sigma of C1. Okay, so what does this imply? So let's consider a situation where the multiplication by the first string class is actually semi-simple. So in particular, in this case, the exponential type conjecture is trivial, just by the elementary splitting lemma. But can we say something further than just exponential type? And the answer is yes. So let's consider Q sigma C1. Then in this case, it is actually just equal to multiplication by lambda to the p on the lambda component of the equivariant singular cohomology. This just follows from the word. Well, this just follows from the fact that in a semi-simple case, you have a decomposition like this. Okay, but by the result of Seidel, that implies that P curvature of the lambda component is also just on the nodes equal to lambda to P. So the corollary of this is that this implies that, in fact, if you consider the residual connection and take its P curvature, it's actually just zero, not just nilpotent. So in this case, by Katz's local logic again, if you know that the P curve is zero for almost all P, then in fact the connection is not just regularly singular, but actually has a full set of algebraic solutions formally. So as corollary, if C1 star is semi-simple, then there's a decomposition of the quantum D module into this form, okay, where again you have some principal part with a projective pole associated to this lambda, but the residual connection to the lambda, to the nebula, has a full set of solution after a potential sort of ramification. Okay, so I think that's all I want to talk about. And I'll stop here.
Thanks a lot. So just open these to questions, but before, just about this very last point. So this was known if the entire thing is semi-simple, right? The entire quantum cohomology.
Exactly, yes. This was known if the entire thing is semi-simple. And if the entire thing is semi-simple, you actually know this without this kind of ramification.
Okay, but now you're saying that if only C1 star is semi-simple, then you can do it just after changing taking the root of T or something.
Yes, yes.
Okay. Okay, so the questions? Let's try. Okay, so can I ask another question then?
Sure.
So is there like known or a guess for categorical versions of this?
Yes, yes. So that's exactly the concept. It's one of my other paper. So I'm glad you asked. So I guess there's a categorical version of quantum operation. So okay, so what is this? So it's some action of partial cohomology, say of some A infinity algebra A, acting on called the Z-mod P equivariant partial homology. So schematically, you can take a version of partial chains where you have like some of P distinguished bimodular entries. So just say this is, let me take the following particular chain model. So consider a partial chain complex of A with respect to the P-fold bimodule tensor product of A. And I consider like the homotopy fixed point of the obvious Z-mod P action here. Okay, I'll define it to be my HH up star. Sorry, this should be Z-mod P equivariant partial homology.
Okay.
Okay, so it erupts like this. So this is the picture if P equals 3. And I interpret the left-hand side as, you know, just bimodule homomorphisms of the diagonal bimodule. I take an element here. I'll just say, okay, it acts just by inserting this phi at each of the sort of P bimodular entries. And this defines the some kind of equivariant action on this chain. And I guess theorem, which is my other paper called quantum string operation for categories, is that this action corresponds to quantum string under, I guess, some suitable versions of open closed maps. Okay, so I guess maybe the hope is that you can use this kind of operation to study P curvature for the Katzarkov-Pantev connection. But there are some difficulties there with dealing with the categorical version, which mostly has to do with that there's like no canonical splitting of the clutch to geometric spectral sequence. We don't even know if it generates in a Z-mod squared case. So there's some, I guess. Yeah, but you know, modulo those, I think you can try to apply a similar idea to sort of prove this result that.
So at some point you had an argument that the quantum cohomology is in degrees 0 to like the dimension, right? Something like that.
Oh, sorry, can you say the question again?
So at some point in your argument, right, if I remember correctly, to prove this nilpotency, you use the fact that the quantum cohomology is in degrees 0 to the dimension.
Yes, it's in bonded degree. Exactly. So that's the difficult thing. So there's like no clear analog for this in the categorical context somehow.
Okay.
It's kind of, yeah, degree argument.
Okay. Thank you. So any other questions? Last chance. Okay. So thank you very much. A very nice talk.
Yeah. Thanks for coming.
That's it for today.